right, so now that we kind of have discussed this idea of a differential equation, just an equation involving a derivative, and connect that to our earlier ideas of integrals and this new notion of an indefinite integral where we don't have limits, let's talk kind of concretely actually evaluating things like these differential equations or just a basic indefinite integral like this. Now, we can certainly recognize patterns in them, you know, if they're simple. But in other situations, we may want to have kind of recourse to technology. So here we'll just show how we can solve these antiderivative problems using Python and SymPy quickly. So first, I'm just going to import the symbolic computing library SymPy as sy. I'm going to create a symbol x, because that's the only variable in any of these expressions is x. All right, so I just need x will be psi.symbol, the string x. And then, for example, I'll define a function. We could understand this as a function that takes in some variable x and returns x squared. So I'm going to define df of x, and that'll give me back x squared. And again, what we're doing is I'm interested in what is the antiderivative of x squared with respect to x. This is, again, an indefinite integral. So what we can do is we can say psi.integrate, which is the integrate. And we've used this before, but we input upper and lower bounds. Now all I have to do is pass it a function, which was df of x, and tell it I want the integral with respect to x, and it gives me an expression back as x cubed over 3. All right, now I have to recognize that that's x cubed over 3 plus any constant, but that's the big idea. All right, we could just try that again with, if we have dg of x, and with something like the sign, I need to use SymPy to actually represent that sign of x. And now if we integrate dg of x with respect to x, we get negative cosine of x. Right, so that's actually symbolically evaluating an antiderivative problem like this. Next thing that we want to do is we want to try and visualize these general solutions to these differential equations.